Okay, so we're going to go over a few different things. The main idea of today is this thing called fundamental theorem of calculus. Some of the rest of the stuff we're going to do tomorrow. So if we look at this theorem 4.5, it says the definite interval. Definite, think about it like defined, exact, we know more about it. The definite interval as the area of the region. What this is going to do is going to take 4.1 and it's going to mash it together with Riemann sums. We're going to see how these two things go together before this page is over, actually. So we got to have continuity, okay? And we got to have a closed interval. Those two things should look familiar. We've seen those on almost all of our derivative theorems, okay? And then we've got some other things, but the whole thing that this is saying is we have this bounded region, and the area of that region is represented by the interval. Okay, this isn't new. I've already kind of told you this when we did Riemann sums. All right? Keep in mind that there's numbers. There are going to be numbers here now. Before we didn't have that. Okay? But before we had plus c, we kind of get out of it when you have numbers here, and I'll explain why. So we have this example right here, and it says set up a definite interval that yields the area of the region. Before, we just kind of estimated what we thought the area might be. And we know that if we do more and more shapes, it's more accurate. But the exact answer of this area is going to be the interval from the lower x value. So I'm going to put -2 down here. And then the higher x value is going to be 2. This is your interval of x's that you're including, because we're not just going to open it up for all the points that could be on this graph. It's just between these two x values.
So is that why you get out of C, because it's just the y-intercept in between there?
Yes, but I'm going to ask you why we get out of C before we're done. You're going to know for sure. But that has some part to do with it, yes. All right, and so then I'm going to write f of x. So I'm going to go ahead and write 4 minus x squared. And then don't forget your dx. You may be thinking, why do we have to write dx? I know it's there. Well, if you don't write it, your statement is not correct. You have to write it. Anytime you see the interval symbol, you got to have dx or d something next to it, okay? So this right here represents this whole area. We're going to solve this in a few minutes. But, sorry, before we do, I want you to take just a few seconds, and write down what you think the area of this shape is, using maybe triangles or trapezoids or rectangles or something. I want you to write down what you think the area is. We're going to see how close you get. All right. Give it your best guess, and let's move on. So we have some special properties, and on each of these we're going to have this if statement, and this is something that has to be true, but I don't want you to get too caught up on this. Like this, if f is defined at x equals a, it just means that that point exists. That's, it's something, as opposed to nothing. What happens here is that your stop and start at the exact same x value. They're the same. That's what this is, the interval from a to a. Why would that integral on that particular interval be 0?
Because it's the same point.
Yeah, it's the same point. So what would your area be?
0.
0. You don't cover any space. Okay, what this would kind of look like on a graph is a vertical line, which has no thickness. That's why your area is 0. So this is kind of a fun little thing. Like if you think about it like this, I could put anything I wanted on here. Now this graph would have to be defined at x equals a, yes. But this has to be 0. It doesn't even matter what's on the inside. Okay? That's a fun little quiz or test problem. Don't, look at this first before you start to do antiderivatives. All right, we have another property that says, okay, if we have this thing that we can integrate on this interval, a and b seem to be different, then if I put the big number on the bottom and the small number on the top, that's not the order that I really want. We don't think of intervals from right to left. We think of them as left to right. What this will do is it kind of switches what you should have, and it will create a negative. So if you were to see an interval like 0 to 2, okay, that's great. And if you were to see an interval from 2 to 0, this one is switched. Okay, so what you would do is you would kind of go back and write it the correct way, but you put a negative in front. We're not really going to deal with that too much today, but I did want to bring it up. And it just has to do with reading from left to right, going from least to greatest, and later on when we get into a formula, I'll come back to that. All right, then we have this third property that says we've got f, goodness, we have f, we can integrate it, and f is non-negative. Okay, meaning f can be 0 or positive. In other words, the y's can be 0 or positive. Then this has to be true. Okay, what is this representing again?
The area?
The area. Okay, so the area is going to be positive. I do want to say something, though, in that the area, when we say the area of this shape, that's always positive. All right? However, and I'm just putting it out here now, and then we're going to wrap up the lesson with the same concept. Your integral could be positive or it could be negative. If the y values are negative, in other words, if your graph goes underneath the x-axis and you have area underneath the x-axis, your integral could possibly be negative. Okay? And if it was all under, it would for sure be negative. So we'll see our answer could be positive or negative. All right? If you're confused about this, I think by the end of the lesson, it'll be clear because I'm going to do an example that shows this. But when we say the area, we don't say the area is negative. We say the integral is negative. So they're not, it's not that area and integral are the exact same, but we find the area by using the integral. Yeah.
So why is it on the third special property, why is it non-negative when there's a b array, which is the large over the small number?
The large over the small is what you want. Okay, are you saying because large over small has negative? It doesn't mean that large and small means that that answer is negative. It means that if you start where things are reversed, what you have to do is put them in the right order, but then switch the sign on whatever you have.
Okay.
And it doesn't mean it makes it negative. It means it switches. If it already is negative, then it's becoming positive. Yeah, this right here does not mean, because what if that did mean that large over small is negative, then all integrals would be negative.
Yeah.
And that's not true. Okay, large over small is what we want. This is just saying if you find yourself where they're switched, put it where it's supposed to be and put a negative in front to take care of the switch. All right, now for those of you that were kind of falling asleep, I want you to wake up because this is a really big deal. Look at this theorem. First of all, it has a name. And you know when we have theorems with names, they're a big deal. We're going to do a theorem right up over this on Friday. But look at the name. The fundamental theorem of calculus. This is a really big deal. A really, 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 really big deal. I mean, it is the fundamental theorem of calculus. Okay? It's about as big a deal as I could make anything at this point. All right? It doesn't mean that it's difficult, though. It just means that it's really taking a lot of what we've done and we're putting it into a new theorem. So this says we have a function, we have continuity, we have a closed interval, okay, all that stuff that we say has to happen each time. And then look, f, capital F, is the antiderivative of lowercase f. This is just like how we talked about capital F last chapter, because we would talk about, our function, lowercase f, and we'd say, well, what happens if you're not taking the derivative, but you're going backwards? That's what we're saying. We're just saying, use this notation. Think about this notation before we look at the formula. Another way to write this would be that capital F prime is equal to lowercase f. All right? In other words, lowercase f is the derivative already, and we see it right here. That's what we know. This is the derivative. We're going backwards. So do what you need to do to bring attention to this little formula right here we call the fundamental theorem of calculus. All right. What this means is that you can take the integral, take the antiderivative, and what you're going to do is you're going to plug in the large number you're going to get something. Then you're going to plug in the small number, you're going to get something else, and then you're going to subtract them. The reason you subtract is almost think of it like this way. This is really oversimplification, but do you remember in geometry where you had to find like the area of a picture frame? And you had to find the big area, and then you had to cut out the piece you don't want? It's kind of like that, okay? You have this shape, and you're going to cut out what you don't want. It's more complicated than that, but I think that might be an easy way to understand it. At least that'll be okay for now. So let's go ahead and rewrite the definite interval from the first problem, and let's see how good your guess was. Okay, so anytime you're doing this now that we have numbers, you're going to start it the same way we did before. So what's the antiderivative of 4? 4x. What about the next part? Minus what?
Negative 1/3 x.
Yeah, 1/3 x cubed. And then how could you check this?
Just find the derivative.
Find the derivative. Now normally we would write plus c. I'm not going to write plus c, and I'm not going to explain it to you. I'm going to have Brett explain it to us by the time we're done. So you better be thinking. All right. I do want you to write this. Write a line, draw a line, and then I want you to put your endpoints there as well, your interval numbers. Because what this says is I've done the antiderivative. Now I've got to actually plug it in. In other words, I got to plug 2 in. Then I got to subtract that, minus, plug negative 2 in. So let's see what this looks like. So I have 4 times 2 minus 1/3 times 2 cubed. Okay, in essence, that's f of b minus, now I'm going to do the same thing with the negative 2. 4 times negative 2 minus 1/3 negative 2 cubed. Okay, this is your answer, by the way, but we do need to actually come up with a real answer. All right. Y'all see where I'm getting all this? Any questions? Okay, so let's go ahead and 8 minus. Okay, I'm going to do the number crunching kind of fast in here. I will say this. If you're horrible at number crunching, you need to practice it. You will never get better if you don't practice it. Okay, if you always use your calculator, you'll just continue to be bad at fractions and all that. If you just try it, and then check with the calculator, you will get better. Okay, so what this ends up being is 8 minus 8/3 and then plus 8 minus 8/3. I think many of you could have gone from here to here, and that's totally fine. You didn't have to do it the way I did it. When I have a mixture of whole numbers and fractions, I like to just go ahead and combine all my whole numbers and then combine my fractions. Those two have the same denominator, so we're good. And now I got to combine these two, so I got to get a common denominator. What's my common denominator going to be? 3, right? The denominator's 3. I'm going to write 3 here. So what does that make the numerator? 48. Therefore, my final answer is 32/3, which if we were to write this as a mixed number would be 10 2/3. So what did y'all think the area was going to be?
I said 10.
10. If you said anything between 9, 10, 11, you were pretty close. This is the exact answer. This is not an approximation. This is exactly. The only way to do this is by calculus or a computer program that does infinitely, that does so many triangles that ends up being the same. Okay, so I want to ask you something. Brett, why do I not need a plus C right here?
Right there?
Yeah.
Because you're plugging in the two values that are the intervals.
Okay, so if I had a plus C here, I would put here, and what would happen to those plus C's? They would cancel out. So there's no need in writing them. It's not even a part of showing your work. Don't write them. When you have numbers, intervals that you're doing your definite integral on, then you do not need to do the pluses. It doesn't matter. It'll always work out the same way. Okay, so let's look at the properties just really quick before we move on. Okay, do you see now algebraically why if these two numbers are the same, our answer would be 0? Yeah, because whatever you get here, it'd be subtract the exact same thing. All right, and so let's look at the second one. What if I change these two numbers to where -2 is on top and 2 is on bottom? What would happen to my two big chunks? They would flip, and then the sign would change, positive to negative, negative to positive, whatever it would be. This third one isn't really obvious here. I'm going to continue that on the next page. All right, so let's look at number 3 on the next page. So this is just a straight up problem. We've seen stuff like this before. Now we have numbers here. Okay, the 5 is the large number, the 2 is the small number. That's how we like it. You know, it's not wrong if it's the other way around, but we kind of want to fix that. So first, antiderivative. What's the antiderivative? Y'all look tired today. All right, that's what you get. Okay, I'm not going to spend a lot of time on this because I think this is something y'all get, but maybe just not wanting to do all the time. Just make sure you do your homework. I'm not giving you an absurd amount of problems, but I think you need to do a certain number of problems so that this kind of becomes competitive. All right, we draw the line, we write our numbers. Okay, now we've got to plug it in. So we're going to plug 5 in. So -3/2 5 squared plus 4 times 5. Your first chunk doesn't have to be in big parentheses. I tend to like to do that because it kind of distinguishes between the two. The second chunk does have to be in big parentheses. Why? Because the negative has to be distributed to the whole thing. All right. Who has our calculator out? You want to do us a favor and tap this all in? You're like, why did I raise my hand? You get to call on someone else to do it with you, make sure that you get the same answer. You just pick that person. All right, while they're doing that, we're going to go ahead and look at 4. Sure. Yeah, pick someone else, sorry. She was too sneaky on that one. Connor. All right, we'll come back to that. All right, let's look at 4. And on 4, notice that it's not set up. All right, so you're going to have to figure out how to set this up. First of all, they give you the parabola. They say x-axis, vertical lines, x equals 0 and x equals 2. So let's actually draw this. X equals 0, x equals 2, vertical lines, and then x-axis, which is the same as y equals 0. I'm going to highlight or darken the part of the parabola, and this is what we're trying to find. So again, what would you estimate this area to be if you just count the blocks? Oh, I mean, I'm just asking the rest of you. You're off the hook on this one because you're still doing your calculator work.
Yeah.
3? Definitely 3 point something, right? Probably not though 4. That seems like that might be too big. Okay, so it's good to have an answer that we think it is so that if we're way off, we can figure it out. For sure my answer should be positive because this graph is completely above the x-axis. All right, so now we've got to set it up. Okay, what are my boundaries for my x's? 0 and 2, and you need to write it where the 0's on the bottom and the 2's on the top. Okay, then we're going to write our function. 2x squared minus 3x plus 2, and then a dx. From here, this problem is like the other, so I want you to try to finish this one on your own. What'd you get, Nico, for this one?
It's negative 39.
Is that what you got?
That's what I got too.
That sounds familiar. We'll come back to maybe why that's negative. Alright, so everybody's working number 4 right now. Working it all the way beginning to end. If it's taking you a really long time to come up with this, you need to practice 4.1 more. Okay, the number crunching here is kind of weird, but hopefully you're where I'm at. Alright, I haven't yet put my second chunk. What do you think is going to happen when we plug 0 into everything? It's going to be 0. That's perfectly acceptable if you know that, just to write 0. We don't really want to do that with all numbers, but with 0 it's fine. 0 is going to be your favorite number. Alright, and so anybody already figured this one out?
10 over 3.
10 thirds. That sounds like I remember this one. I remember it because that's the same as 3 1/3, which is really close to what our estimate was. It's good. If you're given a graph, having an idea of what your answer should be is going to help you kind of see where you might have gone wrong. Alright, so back to this one. Yeah.
Why are you putting 2/3 in there on
Because if I'm going to take the derivative, I need to have something so that when I multiply 3 times whatever I put here, I'm left with just 2. So the trick kind of here is to take your existing coefficient and divide it by your new power. That will always work. All right. And so the negative here comes from the fact that this right here is bigger. In other words, you're cutting out more than you're starting with, if you think about the picture frame analogy. All right? It has to do with, if you think about this graph, you start up here at 4, and you have a negative slope, and you're going to have some area here that's positive. I mean, all area is positive, but your integral up here is positive. But this down here, that's negative. All right? The area itself, like if I said the area of that triangle, that's positive, but the integral is negative. Here's the difference in the question. Let's say we had a velocity versus time graph, and you're talking about someone who's driving their car around town for the day. That velocity is going to be positive when they're driving away from home, and let's say it's negative when they're somehow driving back to home, like they forgot their lunch or they go home for lunch or something like that. There's 2 different questions. One is, how far did they drive throughout the whole day, like their total distance traveled, or how far are they away from their house? Meaning, at the end of the day, how far are they from where they started? Okay, the total distance is like total area. How far are they from where they started? That's the integral. And that's actually more useful most of the time. And so we're going to look more at that as we kind of continue with this. Let's look at number 5, though. You have this graph, and it says find the total area enclosed by this graph. And they give us the interval. All right, and then it says find this integral. And so I want you to see total area and integral. Are these 2 things going to for sure give us the same answer?
Yes.
I mean, thinking about just what I just said. They definitely could, but my question is, are they for sure always? No. If I have area below the x-axis, that area is positive, but in the integral it's going to act like a negative. So it's possible for these 2 things not to be the same. Now, I think we're going to run out of time here. So I want, let's just do B, and we're going to kind of table A. all right, about how we would use our answer here to find that. And I'm not even going to comment on here if they are the same or not, but they don't necessarily have to be the same. So if we were doing this integral 0 to 5 of x squared minus 6x plus 8 dx, do you feel comfortable in finding this interval? Okay, I want you to do it completely on your own. Okay, let's finish going over this one. If you're watching this video, notice I did a lot of work while I was taught. So, what did you get for your final answer on this interval?
20 over 3.
20 over 3. Okay, so what I did here is I went ahead and I completed the square and I wrote this in vertex form, same parabola. If you notice, between 0 and 5, some of this parabola is above and some of it's below. All right? That means you're going to have some area above and some area below. Remember, the area is positive, but when we're doing the integral, these little pieces of area, they're going to add to my total integral, whereas these pieces, or this big piece right here, is actually going to subtract. So I want you to see how you could get a positive or an answer or a negative answer for this. But either way, this 20 over 3 is saying the plus blue and the minus red. Is that going to be the same answer as the total area? If I were to add all three of these up. Like, let's consider these to be piece 1, 2, and 3. What I did here is I added pieces 1 and 3, and then I subtracted piece 2. Okay? Up here, would it be the same if you just added all three pieces? No. Okay? Again, we're still going to table this, but I want you to see the difference. So graphically, what this means is we're going to take the area above the x-axis, and we're going to subtract the area below the x-axis. That's what integrating is. And the good news is, integrating the total integral is way more, we're going to deal with that way more than the total area. Because you may be thinking, how do we do the total area? Well, there's different methods, but we're really not going to focus on that, and that's the good news.